All right, so as I was saying when the video cut off, A is a second corrective factor, and together A and B are known as the van der Waals constants. Of a gas. So our text and other resources would provide a listing of these two values, A and B. The goal of today's lab will be to experimentally determine A and B for a real gas. And so that's what we're after with the exercise that we're doing today. The way we determine them is, by measuring something in the lab. Now, B is essentially the volume of a single molecule or atom of a gas. So not something that we're practically going to measure, right? And A is related to the, if we look at what it's attached to here, it would be the pressure associated with a single molecule somehow of an atom. Again, so we're not really going to directly be able to measure these. And we need to come up with, derive some experimental properties or values that we can more easily measure in the laboratory and associate to these two values, A and B. All right? And that's what the bulk of this exercise that I'm in right now will be, showing you how these constants rely on a couple of experimental values that we can measure. The good news is you'll never have to do this derivation again after I do it for you. All right? The rough news is it's a little bit painful to sit through, but it's an awesome exercise to experience, I think, so that you understand why there's so much math incorporated in your chemistry curriculum right now as well. Okay, so that's a big part of what we're getting into today. Okay, so first, before we go too much further and get into the A and B, if we look at these two equations right here, all right, they both still contain this nRT factor that we would have. So if we were to solve each of those equations that we had, solve the real, quote, V and P for the nRT term, okay, we can combine them, since they're equal to each other, and we would come up with what we call the van der Waals equation. Okay? So while this is, each of these respectively is the van der Waals equation for the pressure or the volume, neither of these is analogous to the ideal gas law up here, where pressure and volume are multiplied by one another to equal nRT. All right? So essentially that's what I'm trying to get to, is this form, but for a real gas. And here's what it would look like. The pressure would now have the A divided by NV squared added to it. So we can see that this would come over to here. All right? And then it would get multiplied by the V. And then the volume would then have the NB subtracted from it. So then that's what would equal nRT. Okay? So this becomes the van der Waals equation. All right? Okay. In order to do the derivation that we're working on today, it would be helpful if I redefine one of our variables, which is, or actually two. If I combine two of the variables together into what's called the molar volume. The molar volume, Vm, is simply the volume divided by N. So we see right here we've got N divided by V. That's just going to be the inverse of molar volume. All right, and it's a little bit more helpful if we can always express volume in relation to how many moles of gas we have. Because we know if we had more gas, more moles, we would have more volume. But the ratio would not change. all right, no matter how much gas we have. So it's a little easier to think about it in terms of that ratio, and then we don't have to have as many n's popping up in this equation. So the van der Waals equation, when I use that substitution, becomes P plus A over molar volume squared equals, or times, sorry, molar volume minus B. And that equals just RT when I've divided through by n. So I've also made this substitution and divided by n on both sides of the equation. That's how this V became this Vm. Okay? And this version of the van der Waals equation is where I'm going to get started with the derivation. All right. The key to solving for these A and B's lies in understanding a little bit of behavior that we haven't seen yet. So I'll just have to tell you about it. Okay? But when people were studying these gases, what we came to understand was that for each unique gas, there's something called the critical temperature. Again, when we get into chapter 11 and we study all phases, then this will become a little more commonplace to us. But the critical temperature is the temperature above which we can no longer distinguish between the gas and liquid phase. Okay, you lose the ability to distinguish between the gas and liquid phase because, if you want to know what's happening, it's because the density of the liquid has decreased to become gas-like. Right? Everything, pretty much, its density decreases as you raise its temperature because it expands. The mass stays constant, but the volume expands. Therefore, the density is decreasing. And a liquid is essentially getting heated up so much and it's stretching out that it assumes a density that is the same as that of a gas. All right? Is there a question? Yeah.
Dr. Steele, so you're saying even at a very high temperature or a very high pressure, when the temperature gets to a certain point, then it's no longer indistinguishable?
Mm-hmm. There is also a critical pressure at which this same thing happens from the gas side. Because the gas, you're compressing it and its density is increasing and it becomes liquid-like. But it hasn't gone through a phase transition. All right. So these are called the critical values. When we cross over this line where it becomes difficult to distinguish between these phases. All right. Not every substance has one, as it turns out, or has one that we can measure in a safe setting. But many substances we're learning do have these critical temperatures and critical pressures. Okay. Now, what's important is that as we approach this critical temperature, okay, the change in the pressure of our real gas starts to stop changing. All right. So as the temperature is changing, we know that from our study of gas laws, the pressure, temperature, and volume are all kind of coupled together. All right. So, but as the temperature is changing, the pressure would also be changing. As you approach this critical temperature, the pressure stops changing. All right. Now, just hearing it that way might not sound too bad, but what that means, okay, for us, so the pressure stops changing as we approach and reach the critical temperature, T subscript C. Okay? So critical temperature, T subscript C, this is what that means. In mathematical lingo, which we need to do, what's, for those of you who've had calculus, what's an expression that we often invoke when we're talking about the change in one variable with respect to another? Derivatives, right? All right. Somebody said derivatives. The derivative of one thing with respect to another. All right. And so if you haven't had calculus yet, I'm sorry that this might get a little bit above your head for the next 15 minutes or so. All right. Actually, the next 5. All right. But that's just the nature of the beast. We can't do certain things in chemistry without understanding certain facets of mathematics, like calculus, differentiation, and integration. Okay, so a derivative really is nothing more than a slope, delta y over delta x, where the delta x gets really, really tiny, and you start to look at a really tiny change in one variable. And so you're talking about instantaneous change of the other variable is the language that we often associate with it. Okay? So the pressure is changing with respect to this molar volume. So what we want to calculate, what we would say in calculus language, is that the partial derivative of pressure with respect to volume. English, how pressure is changing as volume changes, okay, at constant temperature, is equal to 0. That's what's really important, is that you understand that's what I'm saying. All right, this sentence up here. How the pressure of this gas changes is now not changing, all right, at this critical temperature. All right. To come up with this expression then, the derivative, the first derivative of this expression would be, okay, when you take the derivative, for those of you who have done it, if you had an expression like x cubed, the derivative of x cubed with respect to x would be 3x squared. The 3 comes down, we say, as the coefficient, and then the power is decreased by 1. So essentially I need to do that, where P takes the place, of the pressure here with respect to what's going on here. Okay? I'm going to just give you these derivatives. Okay? You can ask your calculus teachers to verify this when you get to there. All right? So the derivative equals negative R critical temperature now. So I've essentially got RT here, divided by molar volume minus B squared plus 2A over molar volume cubed. Okay? So you can kind of maybe start to figure out, if this is new stuff to you, where these pieces are coming from. Here's a Vm minus B that was associated with that guy right there. Here's a Vm cubed, which is associated with that Vm squared and the A that we had there. Okay, that's where these pieces are coming from. All right. Now, what's also true, if you've had some physics or your calculus, right, the classic ways to introduce differentiation are position in physics. How an object's position is changing over time. That's velocity. That's speed. So if you had an equation that told you where a ball is, a ball that's rolling, okay? If you had an equation that told you where that ball is, x, its position, at every time t, the first derivative of that equation is the speed of that ball at each of those times, okay? And then the second derivative, if you take another derivative, is the acceleration, right? Because you could, if you're in a car, you can put your foot on the gas and your position changes, but your speed is also changing. You know, you're going from 0 to 10 to 20. So your speed might not be constant. That's when you have acceleration, okay? So it's kind of odd to think, but what's also true at the critical temperature is that the second derivative of P with respect to Vm is also 0. So how the change is changing is 0. So really, everything is stopped at this critical temperature, in other words. So what we want to do is take the second derivative, delta squared pressure dVm squared at the critical temperature. This is equal to 0. So then the derivative of this expression that we started with or developed up here would be now 2 RTC over Vm minus B cubed minus 6A over Vm to the 4th. All right. Now, how is this going to help us? Again, our goal is to get A and B, which are in both of these expressions. All right. What I'm trying to do are develop some equations that have A and B that I can link to one another, substitute one in for another, or solve for one variable to substitute for another. That's called solving simultaneous equations. All right. It's a common algebra process. At this point, the calculus is done. All right. For those of you who are kind of worried, we're done. All we needed the calculus for was to get these two derivatives. All right. What's important now is that both of these equal 0. So if they both equal 0, we could set the two equations equal to each other, right? And then we'll start to get some simplification occurring, all right? Or we could also see that they both contain RTC. So that's actually how I'm going to proceed. We've got a bunch of different options. We could say they both have Vm, or we could find out how they both relate to Vm. The way I'm going to proceed is to solve both of these for the RTC term, and then set equal to each other. So RTC, so I'm going to go on the left and the right. From the first derivative, RTC would be 2A over Vm cubed times Vm minus B squared. From the second derivative, RTC would be 3A over Vm to the 4th times Vm minus B cubed. There's a lot of commonality or common terms between these two equations, I hope you can see. All right? So you can start to cancel a bunch of stuff out. What's something that someone sees that we could cancel out from the left and the right side of this equation right now? Jimmy?
Vm minus b squared.
Okay, I've got a Vm minus b squared. It's not Vm minus b squared over here, it's cubed, but I can take away 2 of them. So I am going to be left with 1 Vm minus b on that side. Good. What's something else that cancels out? Again, we're ignoring RT in the middle now.
You take it out Vm to the cube on both sides. You have 1 left on that side.
That's right. I'll have 1 in the denominator, unit of Vm left. One more thing. I could take out the A. Yeah, the A can cancel out on each side. All right. So this simplifies itself pretty well. I'm left with, after that simplification, 2. Sorry. I'm actually left with 2 equals 3 over Vm times Vm minus B. So this becomes 2 Vm equals 3 Vm minus B, or B equals that's 3B. 3B equals Vm. Wasn't one of my goals to try to find out how to relate these van der Waals constants to something I could measure? So if I could measure the molar volume of the gas, that would give me the B value right there. Okay? Unfortunately, it's not the easiest thing to measure. All right, measuring molar volume is much more difficult than measuring pressure and temperature values. Obviously, temperatures come to us pretty easily from, a thermometer, and pressures from a pressure gauge that we can stick into our experiment. Molar volume would rely on measuring volume, which isn't that hard, but more difficult knowing exactly how many moles of a gas are present in a sample. And those are usually tied to the pressure and the temperature, so it's the most difficult of the three. So what we're going to do is we're going to use this sort of as a placeholder and continue to see if we can't get A and B in terms of the pressure and the temperature of the gas. All right. All right, and so the first step would then be to use one of the equations that we had earlier. All right, I'm going to go back to the first derivative. The first derivative expression was negative RTC over Vm minus B squared plus 2A over Vm cubed equaled 0. I can now substitute that Vm equals 3B. And so I'll substitute that here, and my equation becomes negative RTC over, this would be 3B minus B, so 2B, right, which would be squared then, plus 2A over 3B, which is cubed. That's going to equal 0. All right, I can sort of put one of these terms on the other side. So I'll have RTC over 4 times B squared. I've made this positive, so technically I've moved it to the right side. But that equals 2A over 27 times B cubed. Now, this isn't getting me a whole lot, closer to my answer right now. What I'm going to do is say, okay, then I'm going to solve for the critical temperature, because critical temperature shows up in a couple of different places. So the critical temperature in terms of these variables would end up being 8A divided by 27 R and B. Okay? So this expresses this critical temperature, this temperature when we lose the ability to distinguish between gas and liquid, in terms of, the van der Waals constants, actually. All right, so actually kind of opposite of what we want. We want A in terms of T and P if we can, or B in terms of T and P. But we've got T in terms of A and B. And then R is the same thing you're used to it being, the ideal gas constant, the universal gas constant. Okay? So now we can substitute this TC somewhere else to try to get rid of T and C and replace it with an A and a B, actually, that are closer to what we're getting at. And we can still continue to use what I just erased, that anywhere that molar volume shows up, it's 3B now as well. So we're sort of building up these substitutants that we can use, okay? These things that we can substitute. All right? So let's go to the van der Waals pressure equation. Way back earlier, the van der Waals equation for pressure was R at Tc over Vm minus B minus A over Vm squared. So now I'm going to be substituting for molar volume and critical temperature. This gets a little bit hairy. R 8A over 2B 27 RB minus A over 3b squared. I had two substitutions here. That's why you see 2b and then a b over there. Okay. And then as I start to simplify, this first part becomes 8a over 54b squared minus a over 9b squared. Aha! We've got similar values for exponents there, b squared. So we can combine these two fractions if we give them the same denominator, right? 54, 9 will scale up to 54, right? If I multiply this by 6, so this is kind of like 6a over 54b squared. So I could then add those two. That would give me 2 a's left in the numerator. 2 divided by 27 would give me a over 27b squared. Okay? Now this would become the critical pressure because we defined it at the critical temperature actually as well. All right? So right now we've got critical pressure in terms of A and B. We had earlier critical temperature, I still have it, in terms of A and B. And we have molar volume in terms of B. So we got our three sort of values relating to the properties of a gas defined in terms of A and B. All right? Thinking of an experiment now where we can observe these conditions would allow us to solve for A and B. But as I said, it's hard to find molar volume. But we can find the critical temperature and critical pressure of a gas. This is something we can watch, all right? And we have a device in the lab here that I'm going to show you. It's located, can't see it on the camera, but it's located back here by this first hood. And we'll operate that in a little bit, where we can measure the critical temperature and critical pressure of a gas. We'll physically see the gas change into a liquid, and then we'll actually see it disappear. Like we lose the ability to see the difference between gas and liquid in the same chamber. Okay? And so that's where we'll be at. Okay? So in order to get A and B, got just a little more algebra to do, where we're going to have to do some substitution of these values into one another. So working with the critical pressure, from the critical pressure being 2a over 27b squared, we can temporarily say, all right, well, A would equal then 27 times the critical pressure and b squared. I can substitute that then into my critical temperature expression, 8a over 27 RB. So I'm going to use this A down here. This is going to eliminate A. And it's going to give me T in relation to B only now. Or B in relation to T and P. Okay? So this becomes 8, if you want to see the substitution, times 27 PB squared over your 27 RB. And we're going to get a lot of simplification. Our 27s are going to cancel. All right? One of our B's is going to cancel as well. All right? And we end up with 8B times the critical pressure over R. It doesn't matter if I write B and then PC or PC then B. You know, it's all multiplication, so it doesn't matter. Okay? So this is equal to TC, keeping that from the left side. So B, the van der Waals constant that we're interested in, equals R TC divided by 8 PC. We now have, if we can measure the critical temperature and critical pressure, we have B, the van der Waals constant then. Okay? So this is one of our final end results that we're after.